Thank you, folks. All right. So OpenStack and building storage as a service with OpenStack. Let's first provide a brief overview of what OpenStack is, understand some of its storage capabilities, review some of the cloud and legacy storage platforms, discuss a few of the key open source projects that we're tracking, and define how you'd architect storage as a service using OpenStack and some of these open source projects. Okay, so OpenStack. OpenStack is a open source software. It's designed to provide you the ability to build your own IaaS, comparative to Amazon Web Services and others. OpenStack is supported by a broad range of companies, and right now it has about 6,000 members in 87 different countries. It is distributed under Apache 2.0 license, and it has a large number of sub-projects that deliver various functionalities. So one of the core projects is Nova. Nova provides the VMs on demand. Swift provides the default object storage, although few other open source projects have Swift-compatible APIs and can be substituted for Swift. Glance is an image management package. It provides you a way to create cloud images, create snapshots. Keystone is its authentication system. It can use both local and it can tie into the enterprise authentication store as necessary. The UI is provided by Horizon, which is the OpenStack dashboard. Quantum provides the network orchestration layer, and Cinder provides the block storage. Okay. Key capabilities that OpenStack is designed to do. Well, if you're familiar with Amazon Web Services, OpenStack is designed to provide an open source competitive version to that. So you can do VMs on demand, provision VMs, snapshot them. It supports multi-tenancy. You can set up quotas for different users. Users can cross tenants, but you can also create networks on demand for per user basis and provide volume to individual users and VMs. You can provide block level volume support, similar to Amazon EBS, and you have a service equivalent to S3, which is Swift, and object storage. It serves few functions in OpenStack. You can use it as a backend for Glance to store images and snapshots, and you can also use it as a general purpose object storage pool. Okay. So let's go ahead and cover what OpenStack needs for its storage. OpenStack has three storage tiers. Ephemeral storage tier, where the disks are tied to the lifecycle of the VM. Persistent one, as you may have guessed by its name. These exist for as long as the tenant exists that created them, and the object storage tier. Okay, so some of the additional details for each one of the tiers. Like I mentioned before, in the ephemeral storage tier, each volume is tied to the lifecycle of VM. It's destroyed automatically when a VM destroy command is issued. It's typically your guest boot volume, and on a small enough guest, that's all that's needed. Now, there's a few different types for providing the ephemeral storage tier. The most common one that we see so far is simply local drives. These have low latency. These have very low cost. Now, the disadvantages, of course, they provide a longer live migration. Now, live migration from local drives is simply a network copy. And there is no guest HA using local drives. Shared storage can be done with multiple approaches. Now, by default, OpenStack does not manage the shared storage for the ephemeral storage tier, with one exception that we'll cover in the next slide. These are just NAS or SAN. You mount them as either block devices or volumes to your compute hosts. And you provide access to a shared storage pool. Now, these typically come at a significantly higher cost, probably about a factor of 3x. But offset it by having more features. Typical feature most vendors offer is thin provisioning, faster migration of volume of guests between the VMs, since all you need to do is shut down an individual guest and start it on another node. No network copy is required. Then you have the ability to do standby HA. If a VM fails on a particular host, you can restart it. But of course, unfortunately, these are not managed by OpenStack at the moment, so that means that you have to statically provision them and control them outside of the OpenStack environment. Okay, so a few things that came into Folsom, and one of them was optional second drive, so you can now have a pair of local drives on your guest. The second drive is presented as an unformatted volume, and it has the same life cycle. Also, boot from volume came in. This allows you to use the Cinder, which is OpenStack equivalent of EBS, and allows you to remove the need for local storage altogether. It's a bit experimental. I think support in Grizzly is going to be much, much better than it is right now. A few manual steps are required to set it up. The interesting thing that you can now control the life cycle of the storage of your VM. So as before, the ephemeral storage drive disappeared. Now you can mark it for cleanup when the guest is deleted, or leave it hanging around just in case you have other uses for it. And now, since Cinder is OpenStack managed shared storage, you can go ahead and manage your storage pool using OpenStack. Okay, so these are the three possible ways you can do ephemeral storage. First one, of course, is local storage, where you just reslice your local drives and offer them to individual VMs, either as block devices or files. Next one is just NFS, where you mount a bunch of NFS shares onto hosts. And the third one is Cinder for boot from volume support. Okay, OpenStack persistent storage. In Essex, it used to be called Nova Volumes. In Folsom, it became a standalone project, now called Cinder. And Cinder is going to be the default storage going forward, although in Folsom both are supported. It provides iSCSI volumes on demand. It's an expandable project. It's designed for vendors to write their drivers in. So roughly 12 to 14 different drivers exist, anything from EqualLogic to Isilon to NetApp, and other storage systems like Nexenta. The basic storage services are going to be offered by your Linux box, which will use LVM to slice the drives into a bunch of volumes and present it as a series of iSCSI targets using generic open source iSCSI target package. Some of the advanced services can be provided by through the drivers. Few of the drivers that we're familiar with are the drivers for Nexenta. Mirantis and Nexenta co-developed them together. We're also have played heavily with the drivers for NetApp and Ceph to use in the block storage tier. So the advanced service providers will provide thin provisioning. They provide native snapshot support, so the snapshot supports will be faster. LVM is a little slow once you have a lot of snapshots involved. Obviously, these guys will have a built-in HA capabilities. All of them offer that. So if you need to have an HA storage, these are the folks to look at. Okay. Persistent storage in Grizzly, what's coming? Well, support for Ceilometer, so metering is coming. Ability to impose different quotas. Ability to clone. Right now, you can create a snapshot. Snapshot is exported to Glance, and then you can download it from Glance and relaunch it. You'll be able to do that directly from. You'll be able to clone and run from Cinder in Grizzly. Ability to have some sort of a scheduled backup activity. and volume scheduling. So what is volume scheduling? It's the ability to decide what type of volume the user will get. Maybe the user should get a higher performance volume or a lower performance volume. Maybe the user should be placed on HA storage or non-HA storage. So these type of scheduling activities are coming in Grizzly. Okay, so what does Cinder look like? Well, there's an API service that provides a REST API for controlling your storage. There's a scheduler that decides which one of the physical devices will be serving your storage. And there is also the volume service itself, the one that on the Linux box will create the LVM and export it via iSCSI. Now, there used to be support for ATA over E, and I think CoreRate is still working on putting it back. And of course, Brocade is putting in support for fiber channels. So iSCSI is not the only thing that's available out there. It's just the most common option. Okay, object storage. So default object storage in OpenStack is called Project Swift. It provides storage via RESTful APIs. It's essentially rough equivalent of Amazon S3. There's few things that it doesn't do, like regions that well, but other than that, it's roughly equivalent. The storage is written to be very, very simple, but it's highly scalable. There's multiple 6+ petabyte clusters out there, so it's known to be very robust. It has limited amount of geo-replication, mostly container-based replication, although few folks like Colony and us have fixes to allow for GeoSwift clusters. Architecture, well, at its core, it is a DHT. If you guys read the Dynamo paper, nothing new there. It's actually a simplified version of the DHT. It's a lot simpler than React and some of its other DHT cousins. But it does have something interesting. It has anti-entropy services. So there's going to be crawlers going through and making sure that your data does not get corrupted, that your data is still there and will replicate and detect failures. Swift is designed with two types of services. There's proxy servers who are responsible for taking in your requests via API, handling the three-way replication, and also performing some of the data consistency checks. And the object servers, the guys who actually physically store the objects on the different file systems. So like I mentioned before, Swift matches most of the S3 functionality. It has its own API, although there is also an S3 API shim. So S3 has better support for regions. The large object handling is there in both S3 and Swift. It's just a little bit different. In S3, large objects are recombined after the upload into a single object. In Swift, large objects are actually containers consisting of many smaller fragments. And S3 has an interesting feature that allows you to transfer the payment costs for the downloads to the person doing the request as opposed to the object owner. That Swift does not have. Okay. So what's there? Well, basic hardware is Linux boxes. It uses XFS. It could use other file systems such as ext4. XFS has a far better metadata operation. So right now, XFS performs somewhat better. Eventually, they'll probably be replaced by ButterFS once ButterFS stabilizes. The key to it is that you pick a very low-cost hardware with lots and lots of drives. But you do use more powerful servers for proxies because the proxies incur higher computational costs. They have to transform web requests. They have to replicate data. So typically, the proxies have more memory and a better CPU. Okay. So Swift actually has three different types of entities it stores. Objects, which essentially stores how much, which essentially stores your object, your data. And it also has containers, which are a Swift equivalent of directories and accounts. So actually, the accounts and containers are databases. They're SQLite databases. So in some of the largest Swift clusters, what folks have done is they've created dedicated storage tiers with slightly faster I/O subsystems, maybe 10 KRPM drives, maybe more spindles, in order to handle the demands of essentially a database server. Sometimes what people do is, if you have enough proxy servers, is simply get a stronger I/O subsystem into the proxy servers and put the account and the container rings onto those. Okay, alternate object stores. Well, so Nexenta took Swift and hacked it up to be able to use with ZFS, and Ceph has a Redis gateway, which provides a Swift-compatible API to the Ceph's Redis object store. Gluster has a project called UFO, which does roughly the same thing. Okay, so let's compare some of the legacy storage needs and some of the newer cloud storage needs. Okay, so what are the traditional storage platform types? Well, there's NAS and scale-out NAS out there, either a single box or a cluster of boxes that serves out a global namespace. There's a SAN, which is just a collection of disks, either via iSCSI or fiber channel, or if core 8 has its way, via ATA over E, that allows you to access block devices across the network. There's shared file systems, which combined with SAN serve roughly the same role as your typical NAS box, although a lot of the newer shared file systems do not rely on shared storage. They're written as network-only file systems. And there's object storage. Okay, so NAS. Typically, you have large boxes, very expensive boxes. So if you have $1 million bank account, this is it. Isilon, iBricks, BlueArc, Sonos, and ONTAP GX are the scale-out guys. And these present very, very large pools of storage behind a global namespace and to an enterprise or some major fraction of the enterprise. They're centralized, and the key to it is, since they have a global name storage, now you have to protect portions of that name storage to prevent other people from accessing it. Well, what we noticed is in the cloud, most people don't really need that huge global namespace. Rather, they want to have lots and lots and lots of little namespaces that need to be managed. So the approach, which I'll describe later on, allows you to create and manage those using OpenStack. Okay, SAN. Well, fiber channel, if you like Brocade, or iSCSI, if you're the rest of the world. And it's usually a tightly coupled collection of storage switches, arrays, and storage management software, especially on the fiber channel side. It's centralized again, very high cost. Again, cloud model is somewhat different. You don't need to have a petabyte-sized frame. You need to be able to manage 1,000 terabyte-size allocations in the cloud. Mostly because you're actually charging people directly for storage, so people use whatever they need and can afford. Again, OpenStack can be used to create such a storage as a service using relatively inexpensive and scalable components. Okay, shared file system. Typically, these are used to complement SAN and as a replacement for NAS. There's some legacy ones out there, Veritas, the clustered XFS, and GPFS that actually perform reasonably well in their target markets. But they do have relatively limited scalability and come at a reasonably high cost. There is a lot of the open source alternatives out there in this area. One of the original ones was Lustre, which was started out quite a while ago. as a high-performance shared file system for the HPC marketplace. There is also Gluster, and now Ceph also can be used as a shared file system via gateway. These are designed to scale a lot higher than a traditional storage subsystem. So no more 8-node or 16-node cluster for Veritas. These often span hundreds, if not thousands, of nodes. They come with open source software and commodity hardware, so they're at much lower cost. And the aggregate performance of these guys is generally better than the old traditional shared file systems. Okay, object storage. This is a pool of storage that has a non-POSIX API, typically a REST-based API, although there's also CDMI standardized API in the works. And mostly these storage subsystems are designed around relaxed consistency. So it's okay for data to be slightly out of sync. That allows you to build a far greater scalable storage pool than you would otherwise be able to do at a much lower cost. Atmos was one of the early systems. I think now every single storage vendor out there, NetApp, Nexenta, everybody else, has a REST gateway to their APIs. So the OpenStack default there is Swift. It has higher scalability than most typical commercial offerings. It comes at much lower cost, and it's just Python code. You can hack it up any way you want it to. Okay, so let's cover some of the open source technologies out there. So Gluster, distributed network file system. Lustre, which is a essentially also a distributed network file system, is just designed for a somewhat different use case of a significantly higher throughput and scale. There's a Ceph, who at its core is a distributed object store, but can play multiple roles, including object storage, block server, and as well as a distributed file system. And there's Swift, which only provides object storage services. Okay, so Gluster. Distributed network file system, and it is just like a few of its other cousins, uses hash algorithms to compute data placement. So which means that the amount of metadata that needs to be shared is very limited, essentially cluster membership, and then Ceph nodes can compute, Gluster nodes can compute where the data should reside. It's designed to be stackable with translators translating from whatever storage pool you have into whatever API you need. There is a native file system that uses, I believe, Fuse to be mounted on Linux kernels and a few of the other operating systems. It also provides an NFS gateway, an object gateway, and nowadays, you can also run Gluster as a replacement for HDFS. We found that Gluster is typically good for mid-sized deployments where you have medium performance needs. And it does have replication-based data protection. So it provides data HA. Now, Gluster has an interesting love-hate relationship with striping. So the early recommendations were, do not stripe. If you're striping, you're an idiot. The later recommendations relaxed it somewhat that says, yeah, stripe, but it won't help unless you have very, very large data, and that's accessed in parallel. So that means that most of the file system performance is going to be based on your capabilities of an individual server. Gluster is very easy to set up. So what we've done with Gluster typically is if we're doing a PaaS-based deployment where we need to offer a shared file system in our platform, we create Gluster deployments on the fly in the VMs and present it as just a shared file system. Works really great up to about 100, 200 VMs. So we typically keep it down to about below 50 to 100. Although in later releases, I believe the performance have been improved and scalability as well. Okay, so Lustre. Project got started a while ago, so unlike some of the other projects there, it does use centralized metadata, which means that metadata management is a bit of a problem. Lustre folks are working on it. I believe there's distributed or sharded metadata services that are coming into Lustre relatively soon. It's essentially network equivalent of RAID 0. There is no network-based data protection. If a particular system is permanently lost, so is your data. So there's a recommendation in the Lustre community to use RAID or RAID Z to protect your data. And if you really, really need resilient data using Lustre, you can use DRDB or some of the other block-level replication protocols to replicate the devices underneath it. It's designed to automatically slice up your data and deliver it from multiple drives. That works really, really great when you have lots of users of your data and your file size is relatively large. It has huge speed, far better than any other project. So if you truly need to deliver tens of gigabytes of throughput out there, there's nothing else that quite compares to it. Metadata performance is a bottleneck. Metadata reliability is an issue. So there are some projects out there that you can use with the current versions of Lustre to be able to shard the metadata. And like I said, the community is working on fixing this issue. It's a great file system. Unfortunately, there is no OpenStack integration there. It's just used when you need lots and lots of I/O. Okay, Ceph. At its core, it's a distributed object store, but there's different access methods to it. You can use it either as an object store using its native API or Swift API. You can use it as a distributed file system. You can use it as a block store. It's mountable via a fuse or eventually in kernel options as well on a bunch of different operating systems. And I think they have a direct shim into QEMU as well. So it's usable by the VMs. It's well integrated into the OpenStack. There is a Glance image connector, one of the few ones that provides an alternative data store to Glance. There is a Cinder connector that can be used for either the persistent or the ephemeral storage tier. And it also has a Swift-compliant API. So it can be used as a uniform storage to replace all three storage tiers in OpenStack. It has good performance characteristics. It does slice up your data, so you'll be serving your data from multiple drives at once, multiple systems. It has good scalability. The reliability is using its crush algorithm works out really well. You can define an arbitrary set of nested failure domains based on your system, rack, network, power, whatever have you. And the algorithm will automatically place the data to make sure that your data access guarantees are preserved. So it probably has the most sophisticated failure domain isolation of any project out there so far. Okay, Swift. Like I mentioned before, this is a default object store. It's a DHT. And it has REST API access only. There is no other gateways available. Its core design is simplicity, scalability, and reliability. The performance, mid-level is being generous. Swift is not designed for high-performance object stores. Proxy servers will become your bottlenecks. If you want to scale out your proxy servers, then your costs go up. So the good news is it's there, it's very easy to deploy, and it scales pretty much without limits. Okay, so some of the use cases, what you can use when. So for NAS, pretty much Gluster, Lustre, or Ceph would work. In a SAN, as a SAN replacement, Ceph will provide and Cinder will provide your SAN replacement capabilities. In the shared file system arena, Gluster, Lustre, or Ceph are the leading open source projects. And object storage tiers, it's Gluster, Ceph, or Swift. Okay, so now that you know what's out there, how can you use it? Well, you can build storage as a service. So what is storage as a service? Well, storage as a service is a multi-tenant service. It presents storage via a defined set of APIs. It abstracts the actual storage implementation, so the clients do not need to worry what storage pool is what. And it's typically a foundation for more specialized functions. Data replication and reliability, backup, document sharing, etc. Okay, so a few of the access methods. You can access it as object, block, or file. Object is probably the more traditional one, as Amazon made that access method very, very popular for storage as a service. OpenStack is a good platform for delivering all of these access types. It has a powerful set of native components. And it's well-written Python code. So if you need to extend it to do whatever you need to, you can do it. Okay. Object services. Well, OpenStack Swift or some of its replacements, such as Ceph or Gluster UFO, can deliver object storage services. So the Swift you typically put behind a load balancer. That load balances some number of proxies that interface to a number of object servers behind it. Now, what can you do with the object store? Well, some of the typical uses are either a cloud drive or a multi-tenant NAS. So, cloud drive. Swift can be used as a backend store, and then you have a large number of commercial clients that have been written to present Swift objects as files on the machines. I think Gladinet is probably the leading vendor out there, although Cloudberry, ExpandDrive, and WebDrive are also out there. Open source, there's CyberDuck, SparkleShare, and Synchrony. I think the only one that's actually usable, unless you're a hacker, is CyberDuck. And CyberDuck is not a drive in itself. It's just a UI interface that provides Explorer-like interface to access the files. Typical use is backup to the cloud. Most of the clients include some sort of a schedule-driven backup mechanism that can replicate certain sets of files or folders into the cloud, or just to share pictures, music, documents. So Box.net equivalent. So if you want to set up your own drive sharing, you can do it relatively easily. Okay, multi-tenant NAS services. Okay, how would we do this using OpenStack? Well, there's few different ways of doing it, and it depends on whether or not you want to provide it to physical hosts or to the virtual guests. There's two ways of doing it, essentially. One is a virtual storage array. You essentially use a VM as a bridge to provide NAS services using some sort of a backing pool, whether it's local drives on the compute hosts or whether it's Cinder. So what you do is Quantum will be used to create a network partition, to create a virtual network for a particular tenant. And then a virtual storage array would be instantiated automatically as a VM in the guest's network. And then it'll be given a set of volumes using Cinder. Those volumes can come from either generic Linux boxes, as I mentioned before, or they can be done via Ceph. Physical storage array. Well, that gets a little interesting. Uh, so uh, the physical storage arrays create a set of problems, mostly around using them in multi-tenant environments. Now, some thought have been put into it on how to make it possible, and it is possible to do that. So, for example, a NetApp filer can be partitioned into some, I believe, 64 to 56 virtual filers. So the key to it is how to create how to add a particular virtual filer to your network. Quantum will create a network segregation, but Quantum right now does not talk well to physical devices. So Quantum will actually have to be extended. Now, the extensions are not complex, but it will have to be extended to provide a network partition all the way to a virtual filer on a single physical box. Then Cinder can be used to create and partition the volumes. NetApp will respond very nicely to Cinder commands, including the ones that involve creation of virtual filer. If your device does not support concept of internal virtualization, then you can only present it as a global storage pool. So that means no per tenant-based segregation. Okay. Multi-tenant iSCSI SAN. Well, Cinder is already a SAN for the virtual guests, so not much is needed there beyond giving a Cinder a reasonably large pool of storage to manage. But you can expand it to manage SAN services to provide bare metal support. Again, you'll be using Quantum to partition your network, and you'll be using Cinder to provision the storage and set the ACLs to provide limited access. Physical hosts will need broader security. Typically, right now, that means that you'll be using a VSA, virtual storage array, which will sit there on the tenant's own network and will present only the storage that the tenant is allowed to see. Okay. So, okay. So far, we discussed OpenStack and its 3 storage tiers, covered few of the open source projects, and described how storage as a service can be implemented using OpenStack. So I think it's time pretty much for Q&A. Okay, so SAN provides a bunch of block storage devices. So you mount it as a block device, right? And a NAS provides a file system, a shared file system. So typically, you do not mount the same SAN device on multiple hosts unless you have a shared file system that will arbitrate the storage access to it. Right? So look at SAN as somebody grabbed your local drives and moved them into centralized storage frame, but they're still your local drives. And NAS is a file system that's been extended to cover multiple hosts.
In some of your earlier slides, you were talking about the features which were projected to be implemented in Grizzly.
Yes.
Now, it sounds like if Grizzly is going to be released on time, it sounds like it's right around the corner.
Yep. The slide deck is a few months old. So, yeah.
Can it be assumed then that all those features will be finished and fully implemented, and Grizzly will be released on time with those features, or?
Those features are currently projected to be in. Most of them have been checked in. There is always a chance that stability of a particular feature will cause it to be evicted. Grizzly is in RC1 right now. It's in heavy testing, so feature development is complete, but if any feature will found to be wanting, the OpenStack community is going to X out that particular implementation.
So I guess the only other thing is that I really appreciate your efforts in
Yep. So we're actually supporting mostly CentOS in our repository. But I think we also helped out the OpenSUSE as well.
It's taking a little time, a little bit longer time than I've been able to use those LCS.
Okay.
Have you looked at any of the billing or rebilling tools?
You mean like Ceilometer?
Yeah, so I was just looking at this
Uh,
because they take into account like different prices of storage at different tiers, like
uh,
so hard drives versus these SSDs versus these.
I have not looked at the proposed. So the Ceilometer integration with Cinder is coming in Grizzly. Honestly, I have not looked at the project to see how extensive it will be. I think combination of the Ceilometer and the primitive QoS, the volume type scheduling, will allow you to do something of that nature. And if it's not there by default, chances are we can just add it.
But Ceilometer is really just for the one type of storage. It's not for everything.
Well, Ceilometer integrates storage usage, right? So Ceilometer will allow you to have a centralized way to monitor usage of your storage and report it out to somewhere. Now, the question is, are your reports going to be fine-grained enough that I can differentiate storage types? I don't know if storage type is tracked. If I had to guess, the answer is probably likely, but that would be a guess. I can double check for you, and if you leave me a card, I can let you know.
So sort of a follow-up on that previous question about what's landing in Grizzly. In Folsom OpenStack, Keystone integration doesn't really work. PKI doesn't work at all.
Wait. What do you mean Keystone integration doesn't work? Keystone?
Well, with Swift, not really. I mean, it's sort of, kind of sort of works, but it has a lot of problems. ACLs don't really work. Like, but my question is that all fixed in Grizzly, or is that sort of unknown, or?
Okay. Unfortunately, I can't really speak to each individual bug. Mostly, I play in Cinderland and Quantum lately, so I don't really know if Swift with Keystone is fixed. I think we even fixed it for Folsom if you take our private repo bits, but I'll need to double check. If you have a specific bug that you want me to track down, I'll be more than happy to do that.
Are you seeing any use, kind of underlying of ZFS on Linux, the kernel mode ZFS?
You mean the version 0.6 of ZFS on Linux? So yes, it's the Lustre community recommends it, but with a note of caution that it's not for production use. I'm still waiting for it.
There's going to be some, maybe it's when we meet again next year. The project's been around for 2 years or so or something.
Mm-hmm.
They were kind of focused on reliability, now starting to get into performance stuff.
So it's an interesting question whether or not you would want to be able to use ZFS as opposed to Btrfs as your potential replacement for XFS.
You get a lot more from it, don't you?
Why?
Code base is it like
Okay.
Z?
Okay. So, okay. Let's take a look at what ZFS is designed to support. ZFS is designed to support split logging capabilities, right? So it certainly can be very, very useful for Cinder. Actually, Nexenta storage with ZFS works really well as a Cinder target. Typically, it gives those few puny SSDs give it a performance heft of about 2 to 3x of a generic slow dumb box, right? So, but you wouldn't want to use it for Swift. Doesn't do anything, right? So their Btrfs would probably be a better replacement.
What more does Btrfs?
Not more. The question is, what do you need to do for Swift, right? So.
Hybrid storage solution. So re-caching on SSDs behind the
So like I said, for Cinder, the ability to have a separate SSD accelerated log would be of a net benefit. For Swift, you would not notice it. Now, there is an interesting question that nobody has answered yet. I know that NASA, I believe NASA sponsored the kernel ZFS implementation, right?
It was the LDL, the Lawrence, maybe Lawrence Livermore.
Ah, Lawrence Livermore. Okay. So, but I'm still waiting for the first person to actually start using it as production and the first person to be sued by Oracle. Until then, I'll stay away from it. Well, no. No. Okay. So they have sued Nexenta, and Nexenta settled, right? So, sorry. Okay. Sorry. What do you have the? Oracle sued Corate and Nexenta. Okay, Corate folks told me that they have been sued by Oracle because of the ZFS usage. Maybe they've lied. Okay.
To get the story straight, so
okay.
NetApp lawyers sent Corate. Corate was investigated using ZFS, and NetApp's lawyers sent Corate if you do this, we'll sue you note. And Corate abandoned the project. But there was never a lawsuit. Subsequent to that, Oracle and NetApp settled out on ZFS.
Okay.
So there's never been a lawsuit from Oracle to any of Oracle's former open source projects. No, from Oracle.
Okay, so that lawsuit, so the lawsuit against ZFS came from NetApp, not from Oracle. That's interesting.
That's correct.
Okay, it's then corrected. Okay, so well then, as soon as version 1.0 comes out, we're going to be benchmarking those bits and see if we can use it. Like I said, we like ZFS implementation. We played with Nexenta fairly extensively. We helped them get their drivers into the OpenStack. It does benefit on the object store, on the block store level. So Cinder is probably a good target for ZFS. Swift is probably not. Although Nexenta may disagree. I'm sorry, which one? Well, we have a representative here from InkTank, not to put you on the spot, Donna, but why don't you answer that question?
To be clear, though, that's still just object is customary, right? Right. Block is not, right? Block is customary.
But that's file system, the project file system. That's not right. And Ceph keeping it free, so I mean it saves what we keep it free, so we can all go over and ask him at the end of his talk.
Ah, okay, awesome. CyberDuck. Yes, that's an open source project there. So a lot of the other commercial ones, I believe GladNet will also do something like that. And most of the commercial ones integrate as a removable drive, so you can just use your regular Explorer to push files back and forth. So CyberDuck comes with its own UI.
By the way, have you seen any tools for, say, replicating between object stores? So say you have your an object storage implementation at your site.
Mm-hmm.
How to get it replicated maybe to a third party or something?
Not to another different Swift cluster, because Swift comes with container-based replication. You can mark each container base for replication, or you can run ring of rings using either the colony or the approach that we've have the code bits out for, the one that's used at WebEx to replicate geographically. So you want to replicate between disparate storage systems?
Yeah. I'll maybe say I've got Swift locally and I want to replicate to Amazon. Keep it sort of a backup of Amazon.
Write a connector. I haven't seen anything out there that would quite do that. No, he wants he wants the containers to go to.
Rackspace with their cloud service, they will let you replicate your.
So I can go Swift to Swift across multiple providers.
Well, the Rackspace is going on right now. Yeah.
But, or
Or to another. Yeah.
maybe
Well, DreamHost is Ceph, right? It's not Swift, right? So I don't think you can do container-based replication between us. Yeah. Uh, uh, the container-based replication is on the back end, right? So you can extend the container-based replication. It's essentially just a synchronous replication daemon running out there to go talk to anybody you want to. And you can do that relatively easily. Probably costs you a little bit less than a man month to do it. But I would doubt if the different projects would get together enough that they would start building in replication schemes to transfer data from one to the other transparently. So I think all of them right now are really, really busy trying to get full geo-replication working. So replicating between disparate object storage system types is just not on the radar, at least not as far as I've seen it. Right. So right now, Swift project is working on geo-replication. I believe Ceph is also working on the geo-replication schemes. So it'll take at least few releases to shake those guys out. Any other questions? Oh, that's it. Thank you.